On the worksheet, I asked you the question to, I gave you a function f of x and y is equal to x squared plus 3y minus 3xy. And then I said that the domain of that function was a rectangle. So that's all points x and y with the property that x is between 0 and 2, and y is between 0 and 1. And then I want to find the absolute max and min. So the idea here is that I can't just find critical points of this function in order to do that. Critical points tell me local maxes and mins, but they don't necessarily tell me about absolute maxes and mins. So by analogy with the calculus of one variable, if I wrote a function down that looked like this function has a local maximum here and a local minimum here. And the second derivative test will pick those points out, but the absolute max and min of the function on the domain that I've drawn are at the endpoints of the interval. So the edge of the domain that I'm evaluating the function on is where the function attains its maximum and minimum values. This would be the absolute max, and this is the absolute minimum. So the idea of checking the edges of the domain is also true for functions of two variables. The idea here is that for this function, if I gave you the domain of the function, which starts at 0 and goes to 2 and up to 1 in the y direction, if this function is going to attain an absolute max or a min, then it has to occur at a critical point on the inside of the rectangle, or it could possibly happen at the boundary of the rectangle instead, right? If this function, you can imagine, if this function was sort of a paraboloid that started low and swept up high, there might be a vertex in the middle somewhere where it reaches its minimum, but the absolute maximum could happen at the corners or on the edges of the domain instead. So I have to look for that.
Sorry, is that for the equation?
This goes with, yeah, this one right here goes with this. That's what this set looks like.
So is that a 2 or a 7 on the x?
This? That's a 2.
Okay.
Oh, this was also a 2. Sorry, yeah. On the sheet. So what I'm going to do is I'm going to reduce this to a smaller problem for a second. So if I asked you a different question, which is, what if I asked you to find the absolute max and min of f of xy is equal to x squared plus 3y minus 3xy. But now I just want you to do it on this set right here, just a line segment that started at 0, 0 and ended at 0, at 2. So I'm just going to give you one line segment. So instead of looking at the whole box all at once, I just give you this curve. It's part of the boundary. And I asked you, okay, this is a function of two variables, but maybe I can restrict, if I take that function and I just restrict it to this set of inputs, what is the maximum and minimum value that it can attain? So what should I do here in order to do that? How am I going to write this in a way where, I mean, really this is like almost, you should feel like this is probably a one variable calculus problem because this is a one-dimensional set that we're feeding into the function. So I might be able to use one variable calculus here. How should I do it? How can I get a single variable? This has two variables in it right now. How can I get a single variable? I could put 0 into y because every point along this strip has a y value of equal to 0. If I was going to do that, I might think about the points on this line segment as having the form t comma 0. So this is called parametrizing the curve. We did this back in calculus 3. I'm going to write a parametric description of the curve, which replaces this two variable thing with a one variable parameterization. So this curve can be thought of as x of t is equal to t and y of t is equal to 0. And then I should probably also tell you some t values that produce the curve for my parameterization here, which would be t is stuck between 0 and 2. And that's a parameterization that starts at this point and traverses the curve until we land at the end, right? So once I've parameterized the curve, if I then take these coordinates and plug them back up into f of x and y, this is precisely what Angel's suggesting, I'm going to get a function of one variable. So if you do that, if you take the x and the y from the parameterized curve and you plug it up into f, you get f of t comma 0 is equal to, okay, t squared plus 3 times 0 minus 3 times t times 0, which is just t squared. And just to emphasize that this is a function that we've extracted from f, so it's a different function, I might just call this g of t, which is the restriction of f to that curve. Now I've made a one-variable calculus problem. I've got a function t squared sitting over this line segment right here. How do I find its max and min? Okay, so g prime of t is equal to 2t. 2t is equal to 0 if t is equal to 0. So that's a critical point. You can second derivative test that if you want to. G prime prime of t is equal to 2, which is positive. So this critical point is a local minimum. G of 0 is equal to 0 is a local min. What else do I need to check to make sure that I've got the absolute max and min of that function? Remember up here, it's not enough just to check local maxes and local mins. I also have to check the endpoints as well, right? So I've parameterized the curve, but now I have to plug in the endpoints as well. This is where, fortunately, we found that one of the endpoints is a local minimum. So we've got one of the endpoints taken care of already. We should also check g of, so I'm going to check the endpoints. So we also check g of 2, because that's the end of our domain that we can reach with the t's, right? T goes from 0 to 2. We've already checked g of 0. If we check g of 2, we get 4. So on that curve, on this curve, the smallest value this function ever takes on is 0 right here, and the largest value it ever takes on is 4 right here. If you want to think graphically about what's happening, it's like the function is actually a parabola. The picture of f sitting over this curve is a parabola starting at 0 and then coming out the board at you. So this point right here would be at the point 2, 4. It's hard to draw that, but that's kind of what's happening. Is it goes this way, it comes out. And that's the edge. Whatever surface this thing is actually producing, it's like you're checking what happened at the edge of the surface. If I took this piece of paper and I said, whatever f does, it produces some surface, and you looked at it endwise, what you're tracking with that curve is the parabola at the edge of the sheet that the rectangle makes. I guess in this case it would look something like that, right? There's 0, 0, and then it curves up to 2, 4 at the edge. Like that. Of course, that's great. We have now figured out what f restricted to this curve has as its maximum or minimum. If I want to check for the absolute max and minimum on the box, I need to check the other 3 sides too. So I have four different optimization problems to do for the price of one. If I want to know where this function attains its absolute max or min on this box, so this is going to be the general procedure. Okay, so the general procedure so if I want to find an absolute max or min, step 1 is to find all the critical points. In this case, I think the critical points turn out to be that real fast. All right, so the critical points of the original function are where the gradient of f is equal to 0. The gradient of f is 2x minus 3y. Is that right? And then the derivative of respect to y is 3 minus 3x. So the gradient of f will be equal to 0. 3 minus 3x is equal to 0, which means x is 1. And if x is 1, then 2 times 1 minus 3 times y is equal to 0 implies that y is 2/3. So the critical point for the function sits right here at 1, 2/3. And then you have to evaluate the function at that point. You can classify the point as an absolute max or min, but if we're just trying to find absolute max or min instead of local, I can just plug those numbers in and check the value of f. F of 1, 2, 3 is 2/3. 1 squared plus 3 times 2/3 minus 3 times 1 times 2/3. Is that 1? 2/3. 2 minus 2, I think. So the function has the value 1 right here. Now we already know that can't be the absolute minimum or the absolute maximum because we've already checked that the function has a value of 0 at this corner and 4 over here. So whatever it's doing at 1, 2/3, it is not absolute max or min. Step 2. Restrict f to the boundary, which means parameterize the boundary. That's what we started doing right here. I need to do it 3 more times to fully characterize what's going on at the boundary, but I restrict f to the boundary pieces. 3. Find the absolute max and min of f on the boundary pieces. If this seems annoying and long, it is annoying and long. If you want to keep going with this exercise, you need to keep parameterizing the boundary. So in the same way that here we parameterize this line segment as points t, 0, if I wanted to check the next edge, which goes from 2, 0 to 2, 1, instead I have a different optimization problem to solve. Every one of these points is parameterized as the point 2, t, where now t runs from 0 to 1. That's the second part of the boundary. And if I plug those numbers into f, I get a different function to optimize. Okay, so if x is equal to 2 and y is equal to t, where t goes from 0 to 1, that would say that f of 2t is equal to 2 squared plus 3t minus 3 times 2 times t. Which is 4 minus 2t. Is that right? Did I do something wrong? 3. Where's 3t? Oh, yeah. 3 minus 6 is 3. Okay. It's early. Yeah.
How did you get the boundary for t? Like, how did you get t is less than 0?
Because if I'm going to write every point on this line segment, noticing that the x value is always 2 and the y value can be characterized by a value t, to start at 2, 0, I need t to be 0. And to climb up the line until I get to 2, 1, I have to end when t is equal to 1. You could actually do this in lots of different ways. There's not a unique way to characterize line segments. Well, this one's pretty easy because last time I checked, a line with negative slope probably has its maximum point when t is equal to 0 and its minimum when t is equal to 1. There are no critical points for a line, right? So along that edge, the surface is just a line. This has its minimum value at t is equal to 1. And that's going to be 1. And its maximum value when t is equal to 0, which is going to be 4. So we go over here and we say, okay, we already knew the 4, so we just replicated information we already knew. So, okay, again, geometrically, parabola that started here and came up to this point, and now a line segment that runs from that point back down to the surface. It doesn't get all the way back down to the plane. It goes from the z equals 4 down to z equals 1. So the parabola came up, a line segment goes back down to here from 4 to 1. There's only going to be one. There's a chance we're going to get a parabola out of this case. So what this is from 0, 1 to 2, 1. Might as well just keep checking. Every point along this line segment can be thought of as having y coordinate 1 and x coordinate t, where t goes from 0 to 2. It does not matter if you traverse this in some sort of like you're always going constantly around the path. It's okay to go backwards. All we're trying to do is figure out the values of the function along that path. And again, we're going from 0 to 2 because I'm starting at t equals 0 and I'm sliding down the path until I get to starting at t equals 0 and then moving until t produces the point that gives us the 2. Maybe this one will be more interesting than a line segment. If x is equal to t and y is equal to 1, then f of t1 is equal, okay, there's a t squared minus a 3t minus plus, that's plus, minus 3 times t times, oh, let's cancel again.
Is that 3t or is
3, oh, it's just a 3. Oh, sweet, we got a shifted parabola. So this is, oh, look, some real work. There's the parabola that comes out of that. Now you can pick your favorite method for figuring out where the vertex of that parabola is, because parabolas have local maxes and local mins at their vertices. What's the vertex? Oh, okay. Well, if you have one tool, use it for every problem, right? So take the derivative, and you get 2t minus 3. There's sort of g prime. So that means 2t minus 3 is equal to 0 will be the vertex. So t is equal to 3 halves. Okay, t is equal to 3 halves. Tells you where that occurs. What's the function's value at t equals 3 halves? How do I find it? Do I have to turn it back into x's and y's and plug it back into f? Or could I just take that and plug it into the version of f restricted to this line? It might be easier if we just take that t value and plug it into this. Remember, this is f sitting over the line segment. Okay, so g of 2/3 is equal to 3 halves squared plus 3 times 3 halves minus plus 3. Did I get that right? Oh gosh, 9/4. Ew. It's too early for 9/4. Minus 9 halves plus 3. So that's, did I do something wrong? What did I blow? Oh. I was like, how the hell did I haven't even added fractions yet. How did I make a mistake before I even did it? Okay. So 3/4 at this point, wherever that, when did we say that was? T equals 3 halves. So somewhere in the middle of this line, it hits t is equal to 3 halves, which I guess happens probably right here. T is equal to 3 halves, and the function value there was equal to 3/4. And then when we got to that edge, well, that happened when t was equal to 0, which gives us a value of 3. I'm just going to claim, without doing it, that this is a line segment. And so that's it. Those are the possible points where the function could take its absolute minimum or maximum value. The critical point, the corners of the box, and any critical point that occurred for the function when you restricted it to the edges. And then you just read off what the absolute max or min is. Don't worry, I'm not doing another example of this. This is for you guys to do. Yep.
I thought you said that g of 0 for the bottom line segment was a local minimum. Or is it both?
Oh, so it's a local minimum for the parabola, but it's an absolute minimum for the function. So the way to think about this is, if you think about the sort of surface that we're looking at here, this is kind of a parabolic sheet. it's sort of anchored at the corner. You can think about it being at 0, 0. And then there's a line segment that runs up this way. And then a parabola that goes up like that. And then from this point, there's another parabola that comes up here and a line segment at this edge. It's hard for me to wave my hands at it, but that's what's going on, right? There's a line segment here starting at 0. That's this line segment. So from 0 to 3, there's a line segment here. Over here, there's a line segment that goes from 1 to 4. And connecting these points are sort of parabolic bits. So it's sort of a tilted parabolic sheet. So that 0, 0 point is the local minimum for this parabola that goes like this, right? So it is the local minimum, but it's also the absolute minimum for the function because that's kind of the anchor point for the whole thing. I know, hopefully,
So it can be both at the same time.
it can. It's a local minimum of the restricted function, but it's also the absolute minimum for the function as well. So in a picture, even in a two-variable picture, the way that that would occur would be if you had a function that looked like this. Right? It's a local minimum of the function, but it's also an absolute minimum because it occurred at the boundary and it's the lowest possible value that could happen. A boundary point can be a critical point is the idea. Okay, now these tend to be long-winded exercises. Basically, you have to remember, anyway, I shouldn't know. You have to remember how to parameterize basically just two different kinds of things. You should remember how to parameterize lines, if you're doing this. And the other thing you might like to be able to do is parameterize circles. So, how do you parameterize a circle? There's a circle sitting in space. Maybe it has radius 2. If I was trying to study an optimization problem where I had a function that I was trying to optimize on a disk, say, we're not even going to do the question right now, but suppose that you have some, well, we'll do the setup, maybe we'll actually solve the problem. If I give you f of x and y is equal to x squared minus y squared, and then I tell you that the domain that I want you to optimize the function on, the domain I want you to find the absolute max or min is that domain right there, a disk region instead of a rectangular region. So including the boundary. I would write that as x squared plus y squared is less than or equal to 4. It's pretty easy to eyeball where the local max or min should occur if it does. Where's the critical point for f?
It's x squared plus on the top.
What's that here? These are different.
No, at the top it's the same equation, right?
No. The way to imagine this is f is a hyperbolic paraboloid floating in space, and then I restrict it to the part of the hyperbolic paraboloid sitting over the top of this circle. So imagine there's this huge surface that runs out this way in this direction and goes down in this direction. And what I'm saying is if I cut part of that surface off so it's just sitting over this disk, where do its absolute maximum and minimum values occur? So step 1 would be to check the critical points. We're not going to check. I'm just going to show you how this goes this time. How would I find the critical points of the surface? Take the gradient. 2x will be equal to 0 when x is 0, and 2y will be equal to 0 when x is 0. So there's a critical point right here. It turns out to be a saddle point. In fact, if you plug that value in, the function has value 0 at that point. 0 squared minus 0 squared is 0. If I want to do the same thing that I just did, and I want to turn this into a one-variable equation to figure out where the other values are, I need to parameterize the boundary. I need to take, okay, well, what if I instead thought about the function as just living on the circle? To turn this into a one-variable function, I need to be able to write down points on the boundary in terms of a parameter t in order to do this. Of course, you guys all remember from 143 how to write down parametric equations of a circle. It was only like 2-3 months ago. What should x of t, y of t be here? If I want that to be x of t, y of t, and this is a circle of radius 2, that would be a good way to do it. Cosine of t, sine t. Of course, I need to modify it for the fact that the radius is 2. Okay, so you do that. You write the circle down in terms of cosines and sines. And notice, that means now you've got the entire boundary curve characterized as a function of one variable t. So g of t, that is f restricted to the boundary curve, is going to be f of 2 cosine t, 2 sine t. And that gets you 4 cosine squared t minus 4 sine squared t. And don't go nuts here. That's not 1. I will helpfully rewrite this as this cosine squared t minus sine squared t, and then call upon your deep knowledge of trig identities to tell me how to reduce that into something I could study. I could, right now, at this point, if I wanted to, I could start studying this for its critical points. Well, what is it? What's cosine squared minus sine squared equal to? This is convenient if you know this sometimes. Like, how can you reduce that to a single function? I'll just tell you. Isn't this one of the ways to write cosine of 2t? Isn't that true? I think cosine squared minus sine squared. I think that's one of the rules that's true. Okay, so now at this point, you've got a small problem to do. Probably we should have t restricted from 0 to 2 pi. Now, if I want to figure out the maximum or minimum values of the function, I just have to figure out where the critical points of this guy are. So what we've reduced the problem to is, now I've given you a function of g of t, which is 4 cos of 2t, and I'm asking you to find the absolute max and min of g on the interval from 0 to 2 pi. You could. Another way to do it, though, where if you wanted to instead, couldn't you just plot the function? The cosine of 2t does one whole cycle between 0 and pi and 2 pi, and has an amplitude of 4. So doesn't it do something like this? So we can use calculus, but sometimes we can productively avoid calculus. Isn't that a graph of the function for cosine of 2t? So it has maximum values here, here, and here. But remember, the values that it's producing, that 0 and 2 pi are the same point on the circle because you've come all the way back around again. And the minimum values happen here and here. And you could just read off. It has a value of 4 when t is equal to 0. It has a value of minus 4 when t is equal to pi over 2. Pi spits out a value of 4. 3 pi over 2 spits out a value of minus 4. If I went back up to the unit circle, what that says is this function has the value here of 4. It has a value of minus 4 right here. It has a value of positive 4 right here, and a value of negative 4 right here. So this is sort of what this kind of optimization looks like. If you want to imagine what the function looks like over the circle on the outside, it's kind of a twisty ring. It's up, and then it kind of comes down like this. So it's got 2 high points, and it sort of scoops down to a minimum on both sides, I don't know how to describe it, like a kind of a knotted ring. Okay, I will say that this topic and the next one I want to talk about are among the least favorite topics that students learn in this class because it's annoying. Unfortunately, it turns out finding maxes and mins of functions is one of the most important things you could do with calculus in the real world. Like, somebody just throws an equation at you and says, I want to know how to make the most profit, which unfortunately lots of mathematics, that's what it's for. This is how you do it. You define some sort of feasible region, And you find absolute maxes or mins on that region. All right. Now I could grind an example here, but I think this is better for you. So build some character for you guys to do this on your own. All right, questions about this before I go on to the next idea? This should feel kind of nuts and boltsy, like, you know, we're back grubbing around with definitions. And you might think, maybe there's a better way to do this. It turns out there is a better way to do it. That's even more grindy, but like it's really a lot more beautiful at the same time. All right. Okay. So this is a preview of 14.8. So this is the notes you have written here. I am going to start with what is actually happening. I'm going to try to explain. If you look on the second page of the, I didn't even hand them out, sorry. These notes that I handed out that are in my hands right now. Oh, I did hand them out. You got them. Okay, so I'm going to start by drawing a picture. And I needed this picture to be accurate this time. So fortunately, somebody left me some yardsticks. All right. Oh, yeah, it's really accurate. Okay. So I'm going to ask the following question. This is a question in an area called constrained optimization. So what that means is I'm going to give you a function that I want to maximize, but I put conditions on the inputs that are allowed. So this is kind of like what we just did with the hyperbolic paraboloid sitting over the top of the disk. I give you what's called an objective function. That is the thing I want to maximize or minimize. In this case, the function f of xy is equal to 2x plus 3y. So you give me a 2x, or you give me an x and y. This produces some sort of value, and I'm looking for x's and y's that maximize that value. But I'm going to throw a monkey wrench in here by giving you something called a constraint equation. What the constraint equation does is it limits which inputs you're allowed to use. So in this particular example, we're going to look at the function x squared plus 4y squared is equal to 16. So I'll plot that one. So this is x squared over 16 plus y squared over 4 is equal to 1 is another way of writing that. So this guy right here is an ellipse. 1, 2, 3, 4, 1, 2. Go this way. 2. Okay, now I spent all the time setting up a nice coordinate system, and now I have to try to draw an ellipse that fits it. So this has 4 units in the x direction and 2 in the y. That's not what I want. And then 2 in the y. So just imagine I drew a nice ellipse there. This is the ellipse that we've drawn. What we're saying is I'm only allowed to plug these points into that equation. So this is my constrained inputs. These are the allowable inputs. If you like, in physical systems, this would be something like things that are possible to achieve with some sort of machine that you're designing, right? Possible like inputs that you can even give the machine. Parameters that are in spec, right? Or physically realistic properties of the materials you're working with. So what I want to do is, subject to the fact that I'm only allowed to use those x's and y's, I'm going to start plugging these numbers into this and trying to detect where the maximum and minimum occurs. So the trick is, what I'm going to do is, I'm going to think about all the different values that this could produce. So if I had something like, what are the x's and y's that can achieve the number 0? 0 is equal to 2x plus 3y. So what I've done is I've restricted this to a level curve of it. Can I achieve the value of 0? Sure. Anywhere y is equal to minus 2/3 x. Right? So if I go, okay, so minus 2/3 would be 3 and then down 2, I think. Is that right? So this line would be 0 is equal to 2x plus 3y. Every point on that curve makes my objective function spit out as 0. Which means I have two allowable inputs where that could happen. This point right here and this point right here, which I could solve for. Those two values on my allowable inputs would produce a value of 0 from the function. Make sense? Okay, let's check another point. What if I put 3 is equal to 2x plus 3y, just to make my life easy? Well, if 3 was equal to 2x plus 3y, that would happen when y is equal to minus 2/3 x plus 1. And that looks like this. So this curve is 1 is equal to 2x plus 3y. So if I continue doing this, this curve right here will happen when 2 is equal to 2x plus, sorry, this was not 1. What did I do here? This is 3. This point right here will be 6 is equal to 2x plus 3y. Does that make sense? I'm just plotting out different level curves of that function. The values on every point in this curve are all 0. The values on this curve are all 3. The values of this curve are all 6. Notice that as the level curves travel this direction, they're getting bigger. So what's going to happen when the level curves finally reach the edge of the ellipse? So that's going to be where the attainable maximum actually sits. There's going to be this special curve out here at the edge. Say right here. Whatever value that happens to have, this is the maximum level curve. Maximum attainable. Right? I can reach this level curve because there's a single point on my allowable inputs that actually sit on that level curve. So this is an attainable point. I can find that point right there. Now, it would be annoying if every single time I wanted to solve a problem like this, I had to draw a picture and draw level curves in order to figure out where that point is. Is there anything that we can think about geometrically that would lead us to a method that we could use to solve this?
The gradient points towards like this.
Right. So that point right there, if you notice, if you draw the tangent line to the ellipse and the tangent line to this line, they would be the same. If I started plotting gradient vectors, just think about that point right there. The gradient vector to the ellipse points this way because gradients are perpendicular to level curves. The gradient to the pink line at that point would go this direction. So the gradient of the ellipse and the gradient of the curve point different directions. But when you get out to the green curve, the gradient of the ellipse and the gradient of the green curve are parallel to each other. They're not the same because they're two different functions, but they point the same direction. So if I wanted to find that point, I could either play a game where I try to cook up a way where this line segment intersects the curve and then I solve for the x's and y's, but there could be lots of places where that happens. And this is like a hard problem. Instead, what I could do is, maybe I could figure out a way where I could just write down, so these are parallel gradients. Maybe I could just figure out all the points where the gradients are parallel to each other, and those would tell me where the possible maxes and mins could happen. Was that?
Did you dot the function
You could, but it's even easier than that. You don't even need to dot the things. Two vectors are parallel to each other when one is a multiple of the other. So what we do is, maybe instead what we could do is, we could find where the gradient of f is parallel to the gradient of the ellipse. So we're going to do one more modification to this, and that, which is f of x and y is equal, what's it, x, what's f of x and y? 2x plus 3y. I'm going to write down g of x and y is equal to x squared plus 4y squared. And then the constraint equation, now the reason I'm doing that is, if you think about the constraint equation we originally had, it was x squared plus 4y squared is equal to 16. That constraint equation is a level curve of this function. That's the function we're going to call g. G is the function that defines the constraint. And all I have to look for now are places where, so here's the big idea. The point where those two lines cross each other has to be where the gradient of f at that point is a multiple of the gradient of g at the same point. So that's the Greek letter lambda, which is traditional. And that thing right there, when this title is in chapter Lagrange multiplier, this is literally the Lagrange multiplier. So the trick of this entire method is I could figure out where the x and y value is that maximizes this function by solving that system of equations. If this equation was true, it would mean the gradients were parallel to each other, and that can only happen where they cross like this. So this dude right here is the core of the method called Lagrange multipliers. And the last thing I'll do today is I'll write out the system of equations we would need to solve to figure out where that point is. So this is all, so when you go to the book and you look at this the notes, and this seemingly confusing picture, that's just what I wrote here. This is what this is trying to show you, is that the two curves intersect each other in the maximal way when the gradients are parallel. It also works through this example in detail. So if I run out of time, that's what's going on. So I'm going to erase this picture. And I'll show you what the equations would be. So essentially what you do is we're going to write that down, and then we're also going to use our constraint equation. So we know that x squared plus 4y squared had better be equal to 16. We also know if the gradient of f is lambda times the gradient of g, that it should be the case that, so what is the gradient of f? The gradient of f is 2, 3. And the gradient of g is 2x, 8y. And so if the gradient of f is lambda times the gradient of g, then that would say we also have the equation 2 is equal to lambda times 2x, and 3 is equal to lambda times 8y. So we have 1, 2, 3 equations to solve for. 3 simultaneous equations. All of these need to be true at the same time in order for me to be at a possible maximal point. These conditions being true tell me that the gradients are parallel. That condition being true is what puts me on the curve I'm actually interested in. So how do you solve such a pile of equations? X squared plus 4y squared is equal to 16. And this is why Lagrange multipliers are usually done by computer. And 3 is equal to lambda times 8y. I need to extract all the possible combinations of x, y, and lambda that make this true. So I think if you took equation 1 and solved for lambda, first thing to observe, does lambda equal 0 make any sense at all as a solution to anything here? No, because then I have 2 is equal to something of 0. So I'm going to be able to manipulate things. Wouldn't that say lambda is equal to 1 over x? If I took the second equation and I remanipulated it, I would get this. Then I could take that value and I could plug it into this equation, which would say 3 is equal to 1 over x times 8y. And I think that means x is equal to 8/3 of a y. So I've used one equation to get a substitution for x, and the next equation for lambda, and the next equation to get a substitution for x. Then I take that information and I plug it up into this equation. Now you should you should be suspicious here that these questions are long and nitpicky because there's like lots of equations you got to plug lots of stuff into, and they are. It's freaking obnoxious. So no question we do in here where you have to do it for real will ever be more complicated than a setup like this. Like the more general technique is used all over the place. I'll finish this example next time, and then once we've done a couple of basic examples, we'll move on to talk about integration of rectangles. This is the single most widely used optimization method in constrained optimization that exists.